Hey, what's going on, everybody? Welcome to the Chapter 10 material. What we're going to be talking about here are rotational kinematics and energy. So really to kick this off, we're going to be going through some of the pertinent equations, or rather really the main topics that were covered in the entirety of Chapter 10, and just some of the processes that we had kind of mentioned or had gone over. And then I have 3 sample problems for things that we are going to do. Okay. So let's get into it. So starting off with this chapter, we need to talk about really our analogs for our linear quantities in comparison to those of our angular quantities. And we're really going to define them now. So we've worked with position, velocity, and acceleration almost the entire semester. But now what we're going to do is say, well, take everything that we have in a very linear sense and put it in a circle. So we're going to define our position by now some change in theta. We're going to define our velocity as something called omega, our angular velocity, and our acceleration, which we're now going to define as alpha. So the way we would actually say each of these is just theta, angular acceleration, and our angular velocity, just really of those 3. But each one of these has their own definitions from a mathematical perspective. So theta, I know theta is something that we kind of see as just, this is our displacement in any amount of radians. So what we're really going to define this as now is visually, if we have our center point right here, and we have some arc that we are considering, let's say this is arc A, or rather S, which is going to be equal to our arc length, some angle theta, and our radius, then we can define theta in terms of the other 2. So we're going to say that our angular displacement, theta, is going to be equal to our arc length divided by our radius, which we're just going to concisely say is S over R. Probably not too often are you going to use arc length. However, this arc length is directly tied to our position that we would move. So if we have something like our X position, and we want to turn it into a rotational analog. So like, let's say we have, I don't know, a spool of wire, and we want to undo that spool of wire. Instead of calculating the length for how much we actually pull out, what we can do is figure out how many times that spool has revolved. And then based on that, we can find out what that arc length would be, or rather the total distance of wire that we would have. Something else we want to define is our omega. So really similar to velocity, this is going to be something where it's the change in our position, in this case, our angular position, divided by the time it takes to do that. And what we're going to find is that this is going to have units of radians per second. Now, a radian, if you guys are not familiar with it, are a unitless quantity. So if you see a problem that's giving you the actual units of it, you might not necessarily see radians per second. You just might see 1 over seconds. Now, while this ends up being the same as frequency, this is something that we will go over when we get to chapter 13, and find that this is, the 2 of them are very, very closely related. And a good note for this as well is that this is going to be specifically our average angular velocity. Okay, now let's talk about angular acceleration. Really, really similar to angular velocity, what it's going to be is the change in our angular velocity with respect to time. And really similarly, we'll find that this is radians per second squared. Okay, So other quantities I want to really define for you guys is what a revolution is, and really what our period is. So one revolution, that's going to be equal to 360 degrees, just one full rotation, which is going to be equal to 2 pi radians. Additionally, our period is going to be the amount of time it takes us to go one revolution. So if we want to end up finding, I don't know, if we have our distance divided by our velocity, which is something we can kind of think about it in a similar way like this, then what we'd have is something like 2 pi divided by our angular velocity, where we can consider this as the distance of one revolution over how fast it is, or rather how quick around we're moving, or how long it would take to get that one revolution. How fast we rotate. Okay. So after we've already defined what exactly these are, if we think about it in terms of how we had defined our position, velocity, and acceleration in the linear sense, one of the first things we did right after that was going to our kinematics. So we're going to find that because both of the definitions for each individual thing that we had talked about, since they seem very, very similar to their linear analogs, we're going to find that their kinematic equations are nearly identical, with a matter of just replacing the pertinent variables. So I think it'd be good to write this out for you guys. So if we have our linear kinematic equations over here, I'll write them out, and these should look familiar to you. So look at our V final is equal to our V naught plus our acceleration times time. Our V final squared is going to be equal to our V naught squared plus 2a times our change in our position. Our change in our position is going to be equal to V naught t plus 1/2 at squared. And then we also get that our position is going to be equal to our V naught plus V final divided by 2 times our delta t. So I'm not going to lie to you, this transformation is going to be very, very simple. So knowing that velocity goes to angular acceleration, distance goes to theta, and then our acceleration goes to alpha, then we're going to be able to see that our omega final is going to be equal to our omega naught plus alpha t. Our omega final squared is going to be equal to omega naught squared plus 2 alpha delta theta. Our delta theta is going to be equal to omega naught t plus 1/2 alpha t squared. And then our delta theta is going to be equal to omega naught plus omega final divided by 2 delta t. The transformation is very simple. However, how do we actually get the true transformations between each of these? What are those relationships? And we're going to find that our change in our position, that's going to be equal to our radius times our delta theta. It just so happened that it's going to be the same thing as what we have here, where instead of s, we are going to use x. For our velocity, this is where it gets a little different, because we have different ways that we can define our velocity, and same thing with our acceleration. So we're going to talk about those now. So there are really 3 that I want to make a highlight about. We have our tangential speed. We have our centripetal acceleration. And then we have our tangential acceleration. So our tangential speed, or our tangential velocity, what this is really going to be is, if we have our circle right here, we have our radius r, and we have some angular velocity that is going clockwise. Then we can say that tangent to the surface, we're going to have some velocity that is entirely equal to our r times omega. This equation you will use quite a bit, or rather for substitutions and things like that. Additionally, our centripetal acceleration is something that we had defined previously as our v squared over r when we had talked about circular motion. Well, if we consider this velocity to be our tangential velocity, then we find that the substitutions give us r omega, square that entire thing divided by r, and we're left with r omega squared is equal to our centripetal acceleration. Additionally, for our tangential acceleration, we're going to find it's an extremely similar transformation as we did for our tangential speed. So our tangential acceleration is going to be equal to r alpha. Now, these quantities are really, really useful for you, or rather these little transformations. So keep note of them. Next, I want to kind of touch on rolling motion. So in rolling motion, there are really a few sort of examples that we can have without starting to get redundant. So if we consider a wheel, let's say, of radius r, angular velocity omega, and then tangential speed v of t, then if this wheel is moving, it's not only rotating, but it has some translational aspect to it. So if you consider the wheels on a car, the car moves as well, or if you just consider the wheels itself, the wheels will move with the car in a straight line, but the wheels will also rotate. So we need to consider two different aspects of its kinetic energy. We're going to have a translational aspect, which is what we've been knowing for almost this entire time, that we've been working with energy. It's our 1/2 mv squared. So we'll say this is our translational. But the new one that we're going to be working with is our rotational kinetic energy. And then we'll talk about their sum in just a second. So their translational velocity, well, since the wheel is kind of moving with the car at all points, it's not rotating when we're considering it like this. At any point on the wheel, we can consider that it's moving at some velocity, which is going to be equal to r omega. And this is going to be the case everywhere that we've drawn a vector. And also everywhere that we haven't drawn a vector. I'm sure you guys get the point there. But for our rotational aspect, well, we're going to need to pick some pivot point or some axis of rotation. And we know with wheels that it's going to be right in the center. So, or at least hopefully it'll be in the center when you're driving your car. So we're going to find that in the center here, our tangential velocity is going to be equal to 0. And we expect that because if we consider our r omega, our r is 0 at our axis of rotation. So this makes sense. And then everywhere else on the wheel, we're going to have a v equals r omega. However, the directionality is now going to be a little bit different. And each of these are going to make a right angle with the radius. So we can draw a bunch of these, v equals r omega, v equals r omega. I'm sure you guys get the point there. But let's say we summed up all of those different vectors that we had just drawn. Well, let's consider these 3 points right here. Well, all the way at the top, what we're going to have is our velocity is going to be equal to not only its rotational aspect, but its translational aspect as well. So this comes out to be something like r omega plus r omega. So we find that all the way at the top of this, we have some velocity that's going to be equal to 2r omega. Now, in the center here at our axis of rotation, we're going to have our translational aspect and our rotational aspect. Well, our rotational is 0 in this case, so it's only going to be dominated by its translational aspect, which is just r omega. And then when we get down to the bottom here, if we draw both of the vectors, we see that one is pointing all the way in the negative x direction, one's pointing in the positive x direction, each with magnitude r omega. Well, they're going to cancel from each other, so we find that the velocity all the way at the bottom is 0 when we sum all them together. Now, this looks really weird, but if you consider that it's moving and rotating, all that kind of happens when we get to the bottom of it. Let's take the top of this candle holder, for example, or a candle cap. When it rotates, if the same point right here hits my hand, it kind of stops for a moment and then is kind of lifted and also moved at the exact same time. It's kind of strange to think about in that regard, but it allows us to be able to talk very, very explicitly about how things like our frictional forces work, or rather even just how we're moving with the actual car itself. The v equals 0 here may look a little weird, but in practice, it makes so much sense. Okay, so going on to the rest of this, we kind of introduced our rotational kinetic energy. I kind of talked about it just a bit beforehand, but what is the actual equation that we're going to define it as? So we're going to say that our rotational kinetic energy is going to be equal to 1/2 times our moment of inertia times omega squared. Okay. So we have not defined moment of inertia up until this point in the semester. What our moment of inertia is, in at least a equation sense, is it's going to be the sum of all the individual point masses of an object. Let's call it a cylinder for the time being, or a large, thin rod. And we're going to multiply each of those individual little point masses that make up the entirety of this rod by its distance squared from its axis of rotation. So let me say this again. These are all masses that make up the body. And this is our distance from our axis of rotation. So if we had something, let's say, I don't know, 4 different point masses that made up the body, then we'd have that our moment of inertia is going to be something like that first mass times that distance from its axis of rotation squared. We're going to have the same thing for the second mass, same thing for the third mass, and then so on and so forth for the rest of the possible masses that we may have. And we're going to find that when it comes to things like these uniformly distributed rods, adding up every single mass is going to be an extremely lengthy calculation for you. So putting this in terms of really bodies that we have where adding up all of these masses is going to be nearly impossible for our sake, we have a bunch of different equations that are kind of given to us. for different types of solids. And they just have their moments of inertia based on where their axis of rotation is. And I mean a very specific thing about this axis of rotation, because let's say this is that rod and it's rotating right in the center of the object. The distance from each end is going to be L over 2, where L is the whole length of the entire rod. Well, if we consider points here, here, and here, well, it's just going to be that distance, that straight line to that axis of rotation. And right here, we would find that this is our R value. So it's going to be different for every point in this. But if we had it all the way about the end this time, then we're going to find that the radii are going to be much, much farther away for the ones that were over here. So our moment of inertia we can expect is going to be a little bit higher, or larger for that matter. So just putting it in terms of the actual equations for each of these. So if it's about the center here and it's about the end here, well, for the center, for a uniformly distributed rod, the moment of inertia is going to be equal to 1/12 times the mass of that rod times really the whatever distance we're considering from the rod. So if we are holding a rod and we are standing all the way at the other end, then this radius would be the whole length of that rod. Additionally, if we had it sitting all the way at the end this time, let me make a clarification. This is about the center again. So if we are all the way at the end, then it would be that total distance. Our moment of inertia for if we are all the way at the other end, it would be 1/3 mr squared. Oh, I forgot to write the 1 there. It's 1/12 mr squared. So some other bodies that we kind of deal with are going to be something like a disk. Well, a disk's moment of inertia will be something like 1/2 mr squared. And we have things like a plate as well, a sphere. All these things are, the moments of inertia for each of those objects are readily available on the internet. You can look them up, and more times than not for a problem, it'll be given to you. So you don't need to worry about that too much. Just know where it comes from and where it fits into the rest of our equations. But one little note I do want to make is, let's say our axis of rotation was right through the center and we're rotating along the long end. How would we treat this? We would treat it like a disk. And the reason for that being, for a disk, our axis of rotation is right in that center, and we're kind of rotating around it. This is the exact same thing for this long, thin rod, except that now we're going to have some depth. So the only thing that's going to change really with that would be the mass of the object, if we're considering that axis of rotation right there. Because the longer, I mean, considering that for every, or the density is the same for the whole rod, then our mass is something that we're just going to increase with length. So that's really all I wanted to do for moment of inertia for right now. This becomes an increasingly important topic for the rest of the chapters, but it's a lot easier in practice. And talking about things that are much easier in practice, conservation of energy. So I do want to define how this rotational kinetic energy kind of fits in with our already defined conservation of energy problems. So kind of putting it in terms of our potential energies, we're kind of making a point about them. We've said before that our potential energy could be equal to something like our gravitational potential plus the spring potential at any point. But it doesn't necessarily mean that both of them would be involved in the problem simultaneously. Same thing kind of works out for our kinetic energy. So now we're going to define our kinetic energy as some, I don't know, translational kinetic energy, excuse me. And we're also going to have some rotational. So defining these extremely explicitly, we get that this is 1/2 mv squared plus 1/2 I omega squared. And kind of going off of the rolling motion example, there's a very specific condition for rolling motion. And it's that if we are not slipping, slipping being that if we had, let's say, the top of this jar or something, instead of us just rolling like we normally would, where if I just went like that, it would have a moment where it just kind of caught and it just completely went through. So if it does not do that, then it holds that our angular velocity will be equal to our tangential velocity divided by our radius. Slipping is something that we're not really going to go too much in, if at all, really. So personally, I don't think you need to worry about this, but do know that this condition will be true if we are not slipping. And the problem will tell you explicitly if we are. But how we would kind of put that into practice is that we say that our rotational kinetic energy, or rather our total kinetic energy, is going to be equal to 1/2 mv squared plus 1/2 I, and then make this substitution, and we get that we'd have something like 1/2 mv squared times 1 plus I over mr squared. And what we're going to find when we start to input this I, this moment of inertia, is since it's always going to be some coefficient, let's say C times mr squared, these mr squareds cancel out from each other, and all we're left with is 1 plus some other number that will have some constant that we're going to multiply our translational velocity by, or translational kinetic energy. So let's say we're dealing with a disk or something, then we'd have that this is like 1/2 mv squared, and then it's 1 plus 1/2 mr squared divided by mr squared. All those would cancel, and we find that the total rotational kinetic energy, or the total kinetic energy of the system, including the rotational aspect of it, would now be 1/2 mv squared times 1.5. So we added essentially an extra half of our translational velocity, or translational kinetic energy, to our total kinetic energy. I hope that makes sense. So let's get into our first problem. So 2 children, Jason and Betsy, are riding on the same merry-go-round. Jason is a distance of r from the axis of rotation, and Betsy is a distance of 2r from the axis of rotation. What we want to find is the ratio of their angular speeds, the ratio of their linear speeds, and the ratio of their centripetal accelerations. So there are a few things about this problem that I want to really highlight. So if we consider this as the merry-go-round with some angular velocity, omega, and the two of them they're both on 2 parts of the carousel, or the merry-go-round rather, that are right next to each other, at least in the same direct line. So what it's giving us is that if this is Jason right here, and this is Betsy, then Jason is at a distance of r, and Betsy is at a distance of 2r. Now, just some relationships I want to note here. Their angular velocities are something that we more or less need to find, but we're not given any explicit numbers in this. So if the merry-go-round goes one full period, we're going to find that they take the exact same amount of time to go all the way around. Because if we now consider this, instead of the actual distance that they go, but some displacement delta theta, well, they just so happen to be in the exact same axis the entire time that they are going around. When in the exact same axis, I mean, just they're in line with each other. Not necessarily that they're completely constrained to the x-axis at all times. So what we can say about this then is that the period of Jason is going to be the exact same as the period of Betsy. Now we know that there's the relationship that, this is really going more into one, we know the relationship that our period is going to be equal to 2 pi over omega. Well, if we know that both of the periods are the same and that 2 pi is just a constant, then we can make the exact claim that the angular velocity of Jason is going to be equal to that of the angular velocity of Betsy. So in other words, this will be true if and only if their periods are going to be equal. So the ratio of their angular velocities, specifically Jason's over Betsy's, which is what the problem is asking, is just going to be 1. Okay. So what about their linear speed, though? So really, this is their v of t. So we're going to find that the tangential velocity of Jason in relation to that of Betsy well, it's going to be whatever radius that Jason sits at and his angular velocity, because we're not slipping in this problem, so this relationship is true. We do the exact same thing for Betsy. And we get that when we do our substitutions, this is just r omega for Jason, and then 2r omega for Betsy. Because since both of their angular velocities are equal to each other, they're just omega, and Betsy's radius away from the axis of rotation is twice that of Jason's. So by taking the ratio of them, it's decently easy to see that this is going to be r omega divided by 2r omega, which just knows that Jason has half of the tangential velocity as Betsy. So we'll circle this. Okay, and the last one we want to consider is our tangential acceleration. Or rather, our centripetal acceleration. So we'll say that this is ACP. So we know that this is going to be equal to v squared over r, specifically our tangential velocity over r squared, that is. So if we want our centripetal acceleration for Jason and our centripetal acceleration for Betsy, and for Jason, we get that it's going to be the v sub j of r, and then the v sub b of r. Both of those velocities squared. We'll make our substitutions. It'll be r omega squared divided by r, which is going to be equal to r squared omega squared divided by r, which is going to be equal to r omega squared. We'll do the exact same thing for Betsy. We get that this is going to be 2r omega squared divided by r, and we get that now we're left with 4r squared omega squared divided by 2r. Oh, sorry, this should be a 2r right here. and then this is going to be equal to 2r omega squared. So just to make this point clear as to where I got the 2r from, these are going to be the respective radii in this part of the equation, and we're going to make our substitutions in the second part. So by taking the ratios, we see that it's going to be r omega squared divided by 2r omega squared, and the ratios of their centripetal accelerations is going to be equal to that of their ratio of their tangential velocities, which is just 1/2. Okay, so problem 2. So if we consider a lawnmower that has a flat rod-shaped steel blade that rotates about its center, the mass of the blade is 0.65 kilograms and its length is 0.55 meters. We want to find the rotational energy of the blade at its operating angular speed of 3,500 RPM, which is revolutions per minute, not radians per minute. And B, which is if all of the rotational kinetic energy of the blade could be converted to gravitational potential energy, what height would the blade rise? Now, I'll get more into B later, but let's define exactly what our system looks like here. So let's say we have our axis of rotation. Let's call it AOR. And we are considering that this is a long steel rod that rotates about its center. So we know that its moment of inertia is going to be 1/12 mr squared. Well, if it has some path like this with some angular velocity, omega, and some radius, r, then we can define our radius is 0.55 meters. And the mass of the blade, which is going to be equal to 0.65 kilograms. So for part A, knowing that we're given omega right here, we can say that omega is equal to 3,500 RPM. And again, I want to note that this is revolutions. So to convert this into the normal units that we have for angular velocity, well, we know that for one revolution, there are 2 pi radians. And then for minutes, if we want to convert to seconds, it's going to be, since this is revolutions per minute, this minute is in the denominator. So we're going to get that this is 1 minute in the numerator now, and then 60 seconds in 1 minute. And this comes out to a value of 366.5 radians per second. Okay. So now that we have all of our quantities more or less defined and in the units that we want them to be, now we can define what is that rotational kinetic energy. And our K rotational is going to be equal to 1/2 I omega squared. Well, we just solved for omega. We know that our moment of inertia is something we just defined, where we have both its mass and its radius, or distance from its axis of rotation. And it's just a matter of plugging the constant in front of it. So doing our substitutions, we get that this is 1/2 mr squared. And then our angular velocity we'll just keep as omega for now and plug in all of the rest of the values in the next step. So this is just going to be mr squared omega squared over 24. Okay, now let's plug in our numbers. So we get that our rotational kinetic energy is going to be equal to our mass, which is 0.65 kilograms. Our distance from our axis of rotation is 0.55 meters squared. Our angular velocity is 3,500 or sorry, not 3,600, 366.5 radians per second squared. And then we're going to divide by 24. And this gets us a total rotational kinetic energy of 1,100.57 joules. So that's part A. For part B, what we're essentially doing is saying if all of our kinetic energy rotational is converted into gravitational potential, find H. So what we can kind of say here is that our rotational kinetic energy is going to be equal to our gravitational potential. And we know that our gravitational potential is equal to mgh. So solving for our height, we get that h is going to be equal to our rotational kinetic energy divided by mg. And now it's just a matter of plugging in our values. So we get that this is going to be 1,100.57 joules divided by our mass, which is 0.65 kilograms, and gravity, which is 9.81 meters per second squared. And we get a total height of 172.5 meters. This is really far. So if you have a blade that is, I don't know, half a kilogram about, and like about 1.5 to 2 feet in diameter, you have yourself there a very, very interesting sort of situation. So yeah, it's an interesting one. Either way, let's go to problem 3. So we want to consider a 2.0 kilogram solid cylinder with respective radius and length. It's released from rest at the top of a ramp and allowed to roll without slipping. See, those kind of conditions are given to us. So the ramp is 0.75 meters high and 5 meters long. When the cylinder reaches the bottom of the ramp, what is the total kinetic energy, rotational kinetic energy, and translational kinetic energy? Okay, so let's actually define what this system looks like. So we're going to have some height here, delta y, some total length, delta x, where I want to note this may look a little strange from a wording perspective, but the 5 meters long is going to be our delta x, not our length of our ramp. So all the way at the top, we have our cylinder. It has its respective radius, call it r sub c, angular velocity, omega, and it also has some translational velocity. There's going to be some angle theta that this entire ramp is at. And we're going to say, for the sake of being able to use conservation of energy, that at the bottom of the ramp, our y is going to be equal to 0. Okay. So this delta x is 5 meters. This delta y is 0.75 meters. But this cylinder right here, it doesn't really do it justice to talk about it or to see it in this light, to see that it actually is a cylinder. So if we draw the cylinder itself, and what we're kind of saying here is that if we are at some radius, let's say r sub c, and some total length L, which is going to be equal to 0.5 meters, and some mass, which is equal to 2.0 kilograms, we're going to find that right through the center of this thing is going to be our axis of rotation. So we are going to have a moment of inertia that's equal to that of a disk, which is going to be equal to 1/2 mr squared. Okay. So for part A, if we want to find the total kinetic energy, then just like we have for conservation of energy problems, let's set up that condition. So we get that the change in our energy of our entire system, potential and kinetic, is going to be equal to the work done by non-conservative forces. Well, for the sake of this problem, we can say that there are no conservative forces. There are no non-conservative forces. So we can say that our initial energy of the system is going to be equal to that of our final. So our kinetic energy initial, our total kinetic energy initial plus our potential initial is going to be equal to that of our kinetic energy final and our potential final. Well, if we're going all the way from the top, from rest, all the way to the bottom with the zero potential, then we see that our final potential is going to be zero and our initial kinetic energy is going to be zero. And we're left with the relationship that our initial potential energy is going to be equal to that of our final kinetic energy. Well, if we're just talking about our total final right now, which is exactly what this quantity is, it's going to be equal to some original mgh, where we can honestly just plug in our values right off the bat, where it's the mass of our cylinder times gravity times the height at which it started at, which is 0.75 meters. We get that it's just going to equal approximately 15 joules of energy at the bottom of our ramp. Okay, so part B is asking, what is the rotational kinetic energy of this? So based on what we had defined earlier on in the video, we see that our total kinetic energy is going to be equal to its rotational aspect and also its translational aspect. So what we had just solved in part A was that this kinetic energy total is actually going to be equal to our initial gravitational potential. So let's make that substitution along with the substitutions that we normally would for our translational and rotational kinetic energies. So we get that this is going to turn into mgh, which is going to be equal to 1/2 I omega squared plus 1/2 mv squared. Well, this omega is going to be equal to our v over r, specifically our translational velocity or tangential velocity. And our masses everywhere after we include our moment of inertia, which is going to be, again, 1/2 mr squared. All of our masses are going to cancel, and we'll be able to do our simplifications from there. So let's actually make that substitution. So we get this is 1/2 times 1/2 mr squared, and then our omega, which is v of t over r squared plus 1/2 mv squared. So before we even do anything else, I am just going to cancel out these masses because we do not need them anymore. So this turns into GH is going to be equal to 1/4. Our radius squared here is going to cancel with the radius squared after we apply the exponent. So all we're left with is 1/4 VT squared plus 1/2 VT squared. And this is equal to 3 VT squared over 4. So we get that the velocity is going to be equal to, we'll keep, so the velocity squared is going to be equal to 4gh over 3. Okay, so the reason that we wanted to find this velocity was so that we could plug it back in to our rotational kinetic energy by knowing that our omega can be transformed into v of t divided by r, that entire quantity squared. So again, going off this and knowing that our moment of inertia is that of a disk right now, we get 1/2 times 1/2 mr squared, and then our tangential velocity squared divided by r squared. Well, these r squareds cancel. And now we can say that our rotational kinetic energy is going to be equal to 1/4 m vt squared, which will be equal to 1/4 m times 4gh over 3. Force cancel, and we get that our rotational kinetic energy is equal to mgh divided by 3, or it's going to be 1/3 of our initial gravitational potential. And putting it this way makes it look really weird, but also makes it all tie into itself pretty nicely. So if we plugged in the values here, knowing that this gravitational potential initial is going to be equal to that of our total kinetic energy, then we know that this is 15 joules. So 1/3 of 15 joules is just 5 joules. And this is the answer. You could also do it by plugging this into itself and just finding out your mass, your gravity, and your height. These are all quantities that we've been given. Okay. And the final thing we want to do is find our translational kinetic energy. So this isn't going to be crazy difficult because we've already solved for a lot of these quantities. But we get that this is 1/2 times our mv squared, which again is going to be 1/2 times our mass, which we had defined earlier as v squared is going to be equal to 4gh over 3. And now we're left with 2/3 mgh, which is 2/3 of our initial potential, which gives us that this is going to be equal to 10 joules, knowing that our initial potential is 15 joules. Okay. So that's really it for chapter 10. The main takeaways I want you guys to get out of this are that we're working with really almost all of the sort of processes that we've dealt with so far with normal systems, like our conservation of energy. We haven't really done too much sum of forces, but we have done rotational kinematics. So kind of working with those, keeping those in the back of your mind and knowing that it's more times than not just a matter of accounting for your rotational sense in addition to your linear sense. You're golden. So with that being said, I'll talk to you guys later and I'll see you guys in the next video. Bye-bye.